From understanding earthquakes to exploring space weather, Earth and space scientists play a crucial role in advancing our knowledge of the universe. Now in Washington, D.C., the American Geophysical Union is convening this diverse community to share research, network, and discuss the future of science. This is AGU 24, and you're watching AGU TV. Welcome to AGU 24, taking place here at the Walter E. Washington Convention Center. I'm your host, Rachel Phillips, and throughout this event, I'll be bringing you the latest in Earth and space science through interviews and event highlights, with new content available daily. From sessions and workshops to networking events, AGU 24 has it all, and AGU TV is here to highlight the most pressing topics and share the most exciting developments. Today, we focus on the theme, What's Next for Frontiers in Science? Exploring the future of Earth and space solutions. We will speak to Kevin Reed, Chief Climate Scientist at the New York Climate Exchange, about the exciting developments in science.
Community engagement, I would say, is paramount. It's actually where everything must start. At the New York Climate Exchange, we're focused on co-developing the solutions that we develop and the research we do directly with our community partners.
Ben Zaitchik, professor at Johns Hopkins University, explains the ethical framework involved in climate change.
Science contributing to solutions, and solutions contributing to science. Right? Our discovery science benefits from the fact that we're engaged in solution science because it points to new questions.
All that and more on this episode of AGU TV. So to make sure you don't miss a minute, here's all the ways you can watch. You can catch the latest episode of AGU TV at the Walter E. Washington Convention Center, in your hotel room at the Marriott Marquis DC on Channel 42, on the AGU 24 meeting website, on the AGU 24 mobile app, and of course on all our social media platforms. And while you're there, make sure to subscribe to stay up to date on all of our geophysical content.
A coronal mass ejection, or CME, is a huge entangled mess of plasma and magnetic field that routinely erupts from the surface of the sun. Essentially, part of the solar atmosphere becomes unstable and begins accelerating at hundreds to thousands of kilometers per second. CMEs routinely impact the Earth. They can do significant damage to satellites and affect power grids or even pipelines on the surface of the Earth.
They're the most energetic phenomenon in the entire solar system. We've been limited, though, in how well we could see them because the coronal mass ejections do the bulk, almost all of their acceleration is in this gap in between what we have traditionally been able to see. Sunset solves that. We can see everything from the center of the disk all the way out to several solar radii with no gaps at really high time cadence.
What's really cool about sunset is we can actually take two pictures at the same time. We can take a picture of the inner part of the corona, which is pretty bright, with a really short exposure. At the very same time, we can take a picture of the outer corona where all the dynamics are happening, where coronal mass ejections and eruptions are happening. And sunset fills the gap between them with really beautiful observations that allow us to actually see dynamic activity that's happening at the sun's surface in one picture.
I am joined by Dr. Ben Zaitchik, the Morton K. Blaustein Chair and Professor at Johns Hopkins University, and AGU's newly elected President-elect. A leading voice in climate science, Dr. Zaitchik combines his expertise in Earth and space sciences with a commitment to advancing ethical, impactful solutions for a sustainable future. Dr. Zaitchik, thank you so much for coming on.
Thanks for having me.
Where do you see the most exciting developments happening in solution science?
So first off, I just want to point out the amazing dividends that solution science has paid. And that's both directions. It's science contributing to solutions, and it's solutions contributing to science. Right? Our discovery science benefits from the fact that we're engaged in solution science because it points to new questions. To point to just a couple of specific things that I think have really taken wing in the past decade, first of all, this really deep commitment to cogeneration. This idea that not everyone might define themselves as a scientist, but everyone's engaged in science. And if we're going to make actionable solution science, that means really putting in the tremendous time and energy, but also just the transcendent experience of working beyond our community, whether that's with local communities, with their environmental challenges, or whether it's with corporations and with larger governments. All of this needs to come together in solution science, and we all benefit from it. And the second thing I'd like to point to is just the maturity of the pipeline of solution science. You have to understand systems. You need to apply that understanding. You need to embody that understanding and embed it within larger decision frameworks. And all of that gets oriented towards the identified problems and opportunities of our partners across society. And again, it works both ways. And so you have a situation where the maturity of the science helps to drive that, and also the maturity of our ability to discuss the science with the people who identify and define the solution space ends up feeding all the way back to improve science. So taken together, I think that solution science has been just a tremendously important initiative within our community.
AGU 2024's theme this year is what's next for science. So what's your next for science? What at this meeting are you most looking forward to?
So there's so many exciting next for sciences, right? And right now, science is always moving in exciting new directions. Right now, there's certainly, for me, and I think a lot of us, a sense that this change is happening remarkably fast. And I think that's not just our perception. I think the pace of innovation, certainly you talk about things like AI, you talk about improved sensing technology, you talk about all of the, some of those components that underlie the science we're trying to answer, those are moving fast, and again, it can create some anxiety. It's also just wildly exciting what's happening right now. And so as we look to all of those possible next, I think that my mind immediately turns to service, right? How can we as a science community harness, leverage, advance some of these technologies, position the core discovery science and solution science questions in a context where you're using these to benefit science, to benefit understanding, and really to benefit society more broadly.
Absolutely. And this meeting is one of those places where the scientific community comes together and thinks about these things and tries to advance science in this way. So what about this annual meeting makes it so special, specifically regarding how it drives climate solutions?
Yeah, so AGU, the annual meeting, right, there's a time-honored and important element of complaining about the annual meeting, right? Like we all complain about the annual meeting. It's too big, it's overwhelming, it's unnavigable, right? There's too much. And all of those things are true. And also, it is the place that it is the single largest regular gathering of Earth and space scientists in the history of humanity. And so the energy that you get with it, like there's nothing like it. And I think it's really important. It's a good time for us to focus on, yes, of course, get your poster done, do what you do, like navigate, like keep your energy up, but all the energy that we consume, like personal energy and otherwise, in making this annual meeting, this hive of activity, I think yields orders of magnitude more energy that drive our community forward. And I think we don't want to forget that the Earth and space sciences, advancing understanding, making that understanding relevant and actionable, gaining a predictive understanding that we can then use to try to inform societal decisions for our planet, and as we look out to the universe, is really, just so wildly ambitious. All right, and it's really perhaps maybe, to me, I think it's one of the most inspiring and audacious things that we do as a species. And this is where we all come together to talk about it. And that just drives so much of what carries us all forward for the year to come.
Wonderful. Thank you so much for sharing this insight with us.
We think that the Antarctic ice sheets are less well known than the oceans of the world. And RAID represents really one of the first opportunities to quickly get direct access to that hidden world.
The RAID provides a platform for quickly making an access hole through 2 miles of ice, faster than any other drilling platform.
We want to push the existing ice core record, which is 800,000 years, back to 1.5 million.
What a deep ice core gives you is a sample of what the atmosphere was doing back to a time when global climate changes had a different character and they moved at a different pace. We'd like to better understand why this was and how the different ingredients contributed to this different regime.
Some of the most interesting questions about Antarctica and about the ice sheets in general fall in kind of this interdisciplinary space, and I think that's kind of where I'm excited as an early career scientist is this potential to address these new interesting questions.
I am joined by Judy Savitskaya and Dan Krupa from Frontier Climate, an organization leading groundbreaking efforts in carbon dioxide removal. They are here to share insights on their exciting global challenge to identify alkalinity-generating rocks and how it helps drive impactful solutions for climate change. Thank you so much for being here.
Thanks for having us.
Yeah. Where do you see the most exciting developments happening in climate science, specifically with regards to carbon removal?
Yeah, so at Frontier, we're generally interested in a broad range of carbon dioxide removal approaches. So we're really focused on a portfolio approach ranging from biomass carbon removal to direct air capture. But one of the areas we've really been focusing on lately is alkalinity-based CDR approaches. This includes things like ocean alkalinity enhancement or surficial weathering or direct air capture with mineral looping technology. So that's one of the key areas that we've really been honing in on, alkalinity-based CDR.
Wow, that is really cool. I find the alkalinity-based climate solutions really, really interesting. A lot of people think about the warming and trying to, invest in things that cause cooling, but the ocean acidification problem is a big one. So I think that's a really good, effort that you guys are doing.
And one of the reasons we're really interested in alkalinity-based is we took a step back and looked for what could reach very large scale, gigaton per year CDR removal, as well as low cost. So those two trade-offs. And really, the natural abundance of alkalinity really led us down the path of looking at these specific approaches that can meet those specific criteria, large scale and low cost.
So this past fall, AGU facilitated the ethical framework on climate intervention. So why is centering ethics so important when it comes to research, funding, and policy in climate science?
Yeah, there's a lot of different pieces of the puzzle here. So there's one that we should address, which is this question of moral hazard. If we use carbon removal, if we can get it to be very, very cheap and very scalable, does that then give us license to continue emitting? So I have good news and bad news, which is that it's not going to be cheap enough to make it not worthwhile to do mitigation. So for sure, mitigation will happen, and it should happen first, and it will happen first. But there's a lot of sectors where there will be continued unabated emissions, and we might actually want to reverse some of the existing impacts of climate change, and carbon removal is a solution to get us there. Another aspect to consider is that some of the cheapest solutions that we're aware of, so that includes enhanced rock weathering in soils and agriculture, anything touching the ocean, a couple of other various types of pathways, they're in an open system, which means they're going to interact with the environment in some way. And that's part of what enables it to be cheaper. You're utilizing some existing system rather than building a box and needing to engineer everything inside of it. So if you're going to have some interaction with open systems, you need to be ultra careful about knowing exactly what the impacts might be, monitoring and measuring and maintaining an understanding of what impacts you're having with the ecosystem.
Yeah, absolutely. And speaking of these impacts and potential uncertainty, how do you balance the promise of solutions with the unknown?
Yeah, I think what we at Frontier try to do is acknowledge that there are a lot of open questions, talk with the right experts who are working on those, and help enable them in whatever way we can through whatever tools that we have available to us to pursue those scientific questions in a way that's geared toward deployment, with the idea being, let's decide what the heuristics are for when deployment is a go or a no-go, or like how we're going to do measurement. Let's actually write down rules on a piece of paper, and over time the science will evolve, and we're definitely going to be wrong in a lot of cases, but to move forward at all, we need to start writing rules so that we can learn what is right and wrong and move forward.
Yeah. I would say Frontier is very much focused on a bit of the deployment aspect. So compiling all the science and research that bubbles up into these promising CDR approaches and startups, but we're really looking to catalyze the deployment And we think a lot of additional learning and research can be done during those deployments to further accelerate the field.
Yeah, absolutely. And at the scale we're at now, these deployments are, even the biggest deployments are small on a climate scale. So we're still learning more than we are, doing a business in the world. Right. It's more about the research. Yeah.
And speaking of moving forward, AGU 24's theme for this year is What's Next for Science. So what's your next for science, and what at this meeting are you looking forward to?
One of the big things that we're really excited for at AGU is to promote our alkalinity challenge, in which we've acknowledged that if we can find low cost, readily available alkalinity sources around the globe, there's this chance for high capacity, low cost CDR to happen at a meaningful scale. But that begs the question, where is all the alkalinity? And so there's only so much we know from the literature or from existing public resources. So we're crowdsourcing it. We're asking for the geophysical community to help us understand where all of these potential alkalinity sources are that could really advance CDR.
Yeah, where are the rocks?
Yeah, where are the rocks? Part of it is that our goal as an organization is the goal of the organization is to put CDR on its best trajectory by 2030. That's the mission that we talk about every year when we do our planning. And one of the big pieces of that is figuring out what pathways are going to work and what pathways are not going to work. And in the alkalinity world, the biggest question for us is does this pathway have enough capacity? Is there enough of this rock in the world at high enough grade, in accessible places, that we could actually, that alkalinity could be a really meaningful part of the CDR solution as a whole. So we want to be able to compare that to direct air capture, for example, where energy is the big resource constraint, or biomass-based sources where the biomass is the big constraint. And so trying to figure out what does the 2050 puzzle for CDR look like, and how can we start making investments now to deploy correctly across these different pathways.
Absolutely. Well, I wish Frontier Climate the best of luck with its endeavors. This is a very, very important, move forward for our field and for combating climate change. So thank you for the work that you do, and thank you for sharing this insight.
Thank you.
Moonshot Goal 8 is built upon two pillars. One, developing science-based weather control, and two, ensuring LC to implement them in an inclusive society that leaves no one behind.
Creating energy-effective result is critical to realize weather control.
Our project aims to reduce rainfall intensity over land by generating rain artificially over the upstream ocean to weaken the rain's impact on land.
We are working to improve the speed of rainfall prediction and estimate potential damages faster, enabling targeted interventions in real time.
To control weather, which is ultra-high dimensional system, we use large ensemble simulations and mathematical sciences.
LC is a key concept for making weather control research socially responsible and connecting people from different backgrounds.
I am joined by Dr. Kevin Reed, Chief Climate Scientist and Director of the New York Climate Exchange. As a trailblazer in climate science, Dr. Reed is driving innovative research and fostering community engagement to create sustainable solutions for combating climate change. Dr. Reed, thank you so much for being here.
Thanks for having me.
So what are the most exciting developments you see happening in climate science?
I think it's about building partnerships, right, across, whether it's working with communities, working with industry, but really building partnerships around how to not only understand climate change, but to develop the solutions that we need for the coming decades.
Absolutely. So why is centering ethics so critical for policy, research, and funding in climate science?
Well, I think it, again, starts with partnerships, right? When you're starting to connect different groups, whether it be community groups or industry, or other stakeholders, it's really critical to come into those discussions and to come into that co-development of solutions and ideas, right, with a shared understanding, a shared set of principles, and that's where the ethics really come in.
Absolutely. And how do you balance the promise of solutions in climate science with the unknown?
Well, the unknown part is that the climate's continuing to change, right? So if we're planning for the extreme events, for example, that we've been facing over the last few years, we have to really start to plan with the fact that those are also going to be changing in the future. And so you can build that kind of unpredictability or that lack, that uncertainty, right, as we typically call it, into the solution space, so that when you develop a solution or you think about a problem, you understand that there's a range of potential outcomes. So if what you've planned for the next event isn't as bad, you could think, oh, we over-engineered. But actually you were prepared and you were successful. And I think a lot of it comes down to really how you discuss the actual solutions that you need.
And AGU 24's theme for this year is what's next for science. So what's your next in science? What at this meeting are you most looking forward to?
Yeah, what I'm most looking forward to is actually how we build those partnerships, right? So we can talk about building partnerships as a pathway for developing solutions and using science to inform solutions. But really looking at how we build those partnerships, what are the kind of long-term aspirations we have? What are folks already doing that we can learn from so we can help to scale? But also, how do we just continue to build the networks and relationships that we need to really be successful in science?
Yeah. And speaking of building relationships, AGU's annual meeting is really powerful in terms of convening the scientific community. So how does AGU's annual meeting drive sustainable solutions to climate change?
27,000-ish people, right, at the same place. The power of convening is really comes through. And it's what I'm looking forward to and what I really use this meeting for in my own work is making those new connections, continuing to build on the previous relationships I have, whether that's with colleagues that I have projects with, or whether that's friends, right, from graduate school, and really build those relationships through the meeting to kind of think about, what are the things that we want to be doing in the next year, the next 2 years, that really not only advance our science, but advance the use of science for society.
So given your role as Chief Climate Scientist at the New York Climate Exchange, how do you think community engagement helps advance climate solutions?
Well, community engagement, I would say, is paramount. It's actually where everything must start. At the New York Climate Exchange, we're focused on co-developing the solutions that we develop and the research we do directly with our community partners. The idea is that when we've developed a solution in collaboration with community partners, that it'll be a solution that not only have they helped shape, but they're going to be willing to use, right? Too many times, I think what happens when academics and industry develop solutions for communities and they do it without community engagement, you end up with solutions that the communities just don't want to use. Maybe it's not in their cultural to use, and the importance of really working with them to not only understand the problem, but actually develop the solutions that you're looking to deploy.
Absolutely. Well, thank you so much for sharing this insight today.
Yeah, thanks for having
me. The Soil Carbon Accrual Project is primarily designed to really understand how these farming systems contrast at scale under our current conditions.
The value of the project to be able to actually in real time record the activities on the farm in the two different systems. This project is measuring conventional farming practices side by side with regenerative farming practices.
Paired eddy covariance towers at each of our 5 sites across California. And these are instrumentation that are mounted up on scaffolding and are powered by solar panels, so they're running all the time. And they're collecting carbon dioxide and water flux data at the ecosystem scale.
But really, we want to help farmers see the benefits of these types of systems and really help them apply them in the field next to that, in the field next to that.
I am joined by Dr. Susan Lozier from Georgia Tech, a leading voice in the scientific community. Today, she'll share her insights on the breakthroughs that have shaped our ability to tackle global challenges and how interdisciplinary collaboration can drive the next wave of innovation in addressing urgent issues like climate change, health, and sustainability. Hello, and thank you so much for being here.
Happy to be here, Rachel.
So what innovative solutions do you see as being critical for addressing the world's most urgent issues? And how can science continue to be a driving force for change?
Thanks for asking that, Rachel.
I'm going to start by just briefly explaining that my area of research is focused on the ocean's role in climate. And so I'm critically interested in how the ocean is being impacted by the warming we see. And everything we see now, if we talk about how can we take care of the ocean warming, the sea level rise, the ice melt, the ocean acidification, every single one of those changes in the ocean stems from the increasing concentration of carbon dioxide in the atmosphere. So I'm sure you've talked to a number of people about the innovative solutions to either draw down CO2 or to reduce the amount of CO2, but I want to mention another one. So when those waters are drawn down at high latitudes during the winter, they carry with them anthropogenic CO2. And the good news is the ocean has drawn down about 40% of the anthropogenic CO2, and that means that it's no longer in the atmosphere where it can contribute to warming. But the bad news is that it's leading to ocean acidification. So the solution, of course, is to reduce the amount of carbon dioxide in the atmosphere. But another solution, though, that's critically needed for those that are concerned about ecosystems in the ocean is trying to understand how that acidification is impacting marine life throughout the ocean and where. So we have lots of measurements of salinity, temperature, less so, the velocity. But really what we need is a large-scale deployment of more what are called the biogeochemistry Argo floats that can really tell us where the ocean acidity is increasing, such that then we might be able to have more marine protected areas or conservation parks. So that's sort of another angle that people don't necessarily think about. Like we all know, like we have to reduce the amount of carbon dioxide. Yeah. But in the meanwhile, we need solutions and new technology that helps us know what are the most vulnerable parts of the ocean. So I'm very interested in development in that area.
And what emerging fields do you see transforming the way we approach problems like climate change, sustainability, and health?
As you may know, Rachel, because you're in this field as well, we haven't done the best job of really engaging a broad, diverse group of people in the United States and globally. And just when we think about how there is mischaracterization of science in general, that also applies to geosciences, I think our next frontier is really trying to figure out how we can engage local communities so that they understand how our work as scientists impacts the health of their community, their own health, such that when the children are in those communities and they go to school, like we're really trying to, provide that pipeline from a very, very much a community engagement piece.
So looking to the future, what role can interdisciplinary collaboration play in shaping solutions to complex global issues?
So as an oceanographer, my entire academic career has been interdisciplinary and thinking about that together, because it's hard to talk about ocean physics without thinking about ocean chemistry, and ocean biology. And also as an oceanographer who studies large-scale global currents, that also includes international collaborations as well. But increasingly, just like the problem I talked about earlier, increasingly we understand that we can't really figure out how that carbon dioxide is getting to the deep ocean unless we understand the physics, which is what I understand, and also that we need to understand the biology. But what this really comes back to is like we know this, we know that we need to have an interdisciplinary study. It really comes back to how we're educating. And so this really touches on my role not just as a researcher but as a dean in a college of sciences. There are some changes in how we are teaching, but we're still primarily teaching along disciplinary lines. And so until we can really sort of break that mold, I think we won't necessarily see the real advances that we need to in interdisciplinary sciences. So for me, it starts, I think I'm going to say academicians like me have that responsibility to really to think more creatively about how we're educating students, undergraduate and graduate students.
Yeah, absolutely. The education is where all of that starts, all of the innovation and all of the science.
Says someone who's in education.
Yes. Well, thank you so much for sharing all this insight with us.
Sure. Happy to.
CUBIX, which stands for the CubeSat Imaging X-ray Solar Spectrometer,
is a CubeSat, a small satellite. In our case, it's about the size of 2 shoeboxes put together, or maybe the size of a boot box. CubeX's primary goal is to look at solar flares. These are the most powerful explosions in the solar system. They release the equivalent of 1 billion hydrogen bombs in the span of just a few minutes. That's more energy than all of humanity will use for 20,000 years in the time span of just a few minutes. It's mind-boggling. CubeX leverages a couple of new technologies for the instruments that we're using. One of them is called MOXIE, the multi-order X-ray spectral imager. We're going to go on the TSIS-2 mission, and we're going to get launched as a secondary. Right now, that launch is predicted to be in late 2025. So hopefully we'll be up from late 2025 all the way through at least late 2026 to observe the sun near the peak of its activity cycle.
That's it for our first episode of AGU TV. But if you missed anything or want to rewatch any of our content, there are plenty of ways to watch AGU TV. You can catch the latest episode of AGU TV at the Walter E. Washington Convention Center, in your hotel room at the Marriott Marquis DC on channel 42, on the AGU 24 meeting website, on the AGU 24 mobile app, and of course on all our social media platforms. And while you're there, make sure to subscribe to stay up to date on all of our geophysical content. So we've covered the frontiers, but what about the policies supporting them? As Earth and space scientists work to bring real change to the world, we'll have more insights tomorrow on how. We'll see you there.